So the next group of problems looks like it dealt with topics in combinations, permutations, and probability. Um, Probability we'll get to here at the end. I'm going to discuss permutations and combinations first, because there tends to be a lot of confusion over this. Permutations, order matters. So this is like, oddly enough, in a combination lock. The order that you dial the numbers on a lock matters, so those are actually permutations. Or if you are awarding medals for first, second, and third place, who gets first, who gets second, who gets third place matters. Most likely the notation your professors used fell into the category of sometimes written like this, where n is the total number of items you can pick from, k is how many you're picking. Sometimes it gets written like this, which is a little bit older notation, and I'm not sure if you saw that or not. But either way, the way we calculate it is it's n factorial over n minus k factorial. And where we see this would be, for example, in the problem where you were being asked how many three-digit numbers can be formed using the digits 2, 3, and 4 without repetition. So with permutations, a lot of times people like to draw. So this is without repetition. People like to draw spaces for the things that they're doing. So we want a three-digit number, so there are 3 spots. In the first spot, there are 3 choices. But now, when I move to the second spot, I used one of those numbers, so there are only 2 choices in the second spot and 1 choice in the third spot. And if I multiply those together, I get 6. Well, this would be the same as if I did 3, E3, or depending on the notation that your professor used, where I have 3 items and I'm picking all 3 of them. That would also give me 6. The other possibility is what's called a combination, and here order does not matter. This would be an example of if you're picking teams in gym class and you're, out of a class of 30 people, you have to pick 15 of them. It doesn't matter what order you pick those 15. You just pick them. In terms of notation, you could see it as NCK, again, where N is how many total you're picking from and K is how many you're picking. Or the more common notation now is this. Or because of how often we use combinations, you'll also see it written like this with no C, just an N over a K inside of their own parentheses. Those are all ways of notating combinations, but all of them are found by us doing n factorial over n minus k factorial times k factorial, which is also the same as doing the permutation for nk, all divided by factorial. The reason for that is the permutation takes into account the order mattering, which means there are repetitions in how we pick things if the order didn't matter. If we had first, second, and third out of 10 people, there's 6 ways people can win, or I'm sorry, if we have first, second, and third, there are 6 ways of that with the 3 people. Or if we had 10 people, there'd be 10 times 9 times 8 ways. But what if those same 3 people came in a different order of first, second, and third? Dividing by the k factorial removes the repetition of 3 people in just a different order. Combinations don't come up in this problem because with repetition, if I think in terms of the 3 spots, again, in my first spot, I have 3 choices, 2, 3, or 4. But then since I can do repetition, I can also do 3 and 3, which gives me 27. So an example of combination, so we had a permutation here, and then this doesn't really have a name to it because we have the repetition. But a combination would be, for the example, where you're asked to pick 4 men and 3 women from a total of 10 men and 9 women for sales reps. So in terms of picking the four men, if we focus on that part, it doesn't matter what order we pick the four men. So this, for the men, that would be where we're doing a combination where we have 10 men and we need to pick four of them, which gives us 210. And then for the women, again, we have 9 women, we need to pick 3. It doesn't matter what order we pick them in. So that would be a combination of 9 women, choose 3 of them, which is 84. And then since I'm doing both of these at the same time, if I multiply 210 times 84, I get 17,640 different ways I can select those 7 people. So then we have a probability example here with classic example of marbles in a bag. And these are pretty basic probabilities. I shouldn't say basic. These are actually called simple probabilities, where what we care about is the number of events that we look for compared to the total possible events. So if we have 3 red marbles and 8 green marbles, that means we have a total of 11 marbles. So if I want to know the probability of picking a red marble, that means I want to know what's the probability of a red compared to total. Well, there are 3 red to 11 total, so 3 to 11 is our probability. Now, if the professor wants that as a percentage, you just do 3 times 11 times 100%. 3 divided by 11 times 100%. Or if your professor wants it as a decimal, you just do 3 divided by 11. But 3 to 11 is a perfectly proper notation for the probability because it is a value between 0 and 1. So then probability of a green marble, I'm looking at I want green out of the total possible events. Well, there are 8 green marbles to 11 total marbles. So the probability of a green is 8 to 11. And then when we have probability of a purple marble, that means I want purple out of the total events. Well, if we look, there are no purple marbles. So that would be 0 out of a total of 11 marbles. So there's 0 probability of us choosing a purple when there aren't any purple there. Then we have the case of what if we're asked the probability of a red or a green. There are 2 ways of looking at it. The more mathematical way is, well, that means I want the probability of a red or probability of a green. And those are mutually exclusive or independent events. I can't have something that could be both. So when we have them as independent events like this, that means I would want the probability of a red plus the probability of a green. If it were said and, this would be a times, because it says or, it's a plus. And that's only true when we're dealing with independent events where I can't possibly have something be both at the same time. But a marble can't be red and green at the same time, at least as we're told we only have red marbles or green marbles. So we already figured out the probability of red was 3 over 11. Probability of green we already found was 8 over 11, which gives us probability of picking red or green as 11 to 11, which is 1. Well, that actually kind of makes sense because we're being asked what's the probability of picking a red or green marble out of a bag that only contains red or green marbles. So as long as we pick a marble, it's going to be red or green. So there's a 100% probability of doing that. So then there was binomial expansion. Binomial expansions, your professor probably covered this as part of using the binomial theorem, which involves using combinations to figure out coefficients. Most likely, your professor wrote something like x plus y raised to n, that's the sum, where k goes from 0 to n, of a combination n choose k, x to the n minus k, y to the k, which really doesn't make much sense to most people because this takes doing series and doing combinations and putting them together. The key here is to remember this is a combination. So if we were looking at this problem and trying to think of it in terms of this, what this is really saying is that this is the sum, where k goes from 0 to 6, of the combination 6 choose k of 4x to the 6 minus k times 5y to the k. Which then, if k is 0, I'd have 6 choose 0, 4x to 6, 5y to the 0. And then when k is, I have plus because it's a series. When k is 1, 6 choose 1, 4x to the 5th, 5y to the 1st. And then when k is 2, 4x to the 4th, 5y squared. When k is 3, 4x to the 3rd, 5y to the 3rd. When x is 4, there's a lot here. 4x to the 2nd, 5y to the 4th. When k is 5, combination 6 choose 5, 4x to the 1st, 5y to the 5th. And finally, the last one of combination 6, 6, 4x to the 0, 5y to the 6th. Then going through and most likely using your calculator to do these combinations of 6 picks 0, 6 picks 1. Again, these are combinations here. Alternatively, and the way I typically do it is I normally won't write it out like this. What I will normally use is I will use what's called Pascal's triangle. Pascal's triangle is a very powerful and very information-rich picture for us. What we care about is it actually will give us the values of those combinations. What it is we start with a 1, then we're moving down to create a triangle. And every time I move down in the next row, each number is the product of the two numbers above it. So I only have 1s then. Well, this is 1. The middle number here is going to be the product of the 1 and 1 above it, or sum, sorry, not product, sum. So 2 and 1 is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1. 4 plus 1 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Oh, I might as well go ahead and go one more row further down here. 1, that's 6, 15, 20, 15, 6, 1. And what I care about here is each row is a power of our binomial expansion. So this would be n is 0, it's 1, it's 2, it's 3, it's 4, and it's 5, and it's 6. So what these right here are the coefficients that I'm going to use in place of doing the combinations. So then when I look at 4x plus 5y raised to the 6th, instead of saying 6 choose 0 when k is 0, well, that's going to be 1. 4x to the 6th, 5y to the 0. Then 6, 4x to the 5th, 5y to the 1st. Then 15, 4x to the 4th, 5y to the 2nd. And then the 20, 4x to the 3rd, 5y to the 3rd. If you notice, the powers for my 4x part are starting at the n and going down, and the 5y are starting at 0 and going up. That's how this will always work. That's 15, 4x squared, 4th, and then 6, 4x to the 1st, 5y to the 5th, and 1, 4x to the 0, 5y to the 6th. Then I trust your ability to be able to actually find for the 6 and 5 to the 6 and all of that, do all of that multiplying if your professor requires it. And finally, finding a sum. My best advice I can give is actually write out the first few terms of this series, because it'll help you figure out, is this arithmetic or is this geometric? And then it helps you just visualize what's happening, because This is not a notation that most people are comfortable with the sigma notation here. So if we write out the first few terms, well, it starts when k is 7, so if I plug 7 in, I have 21 minus 9, which is 12, over 2. And then if I plug in 8, 24 minus 9 is 15, over 2. I plug in 9, 27 minus 9 is 18, over 2. If I plug in 10, I get 30 minus 9, which is 21, over 2. And that's going to keep going. Well, what I can see here is that I have a common difference of I'm adding 3 halves each time. Now, if you notice, I really didn't simplify things here because it's actually easier to see a pattern if I do not simplify. So that's what would be my recommendation is if when you're writing this out, don't do a lot of simplifying. Just do enough, just a little bit to make it a little easier to look at, but it'll be easier to see a pattern without a ton of simplifying. So I know it's an arithmetic series because I have a common difference. I know my first term is 12 over 2, which is 6. To find the sum, then, I need to know how many terms does this end with, and then what's the last term. So to figure out the last number of terms, I know I start at 7 and I go to 44. So n is going to be 44 minus 7, and then it's going to look weird, plus 1. And the reason for this is if you think about it, if I count 1 to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's 10 things I counted. But if I do 10 minus 1, that's 9. So I have to add 1 to include my first term, which is why we have to do that plus 1, is it includes that first term. Because if I just do 45 minus 7, it ignores the fact that I'm using the 7. So to find n, it's that last thing I plugged in minus the first, and then add a 1 to include the first term. So my n is 38, which then means that a sub 38 is my first term plus my common difference times n minus 1, which gives me that my 38th term is 123 over 2. So then from all of this, my sum is going to be 1/2 times n times my first term plus the 38th term, which gives me that the sum is going to equal, I guess I should actually go ahead and type this on the calculator to find out here. And 1,282.5.